Do you have any questions about stuff from last time, or today was polarity and intermolecular forces were the topics?
I have a question. I was reading it. It was one of the homework problems of my conference. Do you say it well?
Do you remember what the general topic was?
There was something about ranking boilerplate, and it gave you 4 structures, and you had to rank it from highest to lowest.
Okay. Let's see. Wait, I'm in chapter 2, which you're not in yet. Chapter 1. Yeah. Let me open this. All right, so let's see. Maybe that one?
Yeah, I was that one.
Okay, boiling point, from highest boiling point to lowest boiling point. Okay, so what do we need to know if we're going to rank molecules according to melting point or boiling point? How is that? What do I need to know about the molecule? The intermolecular forces that it has. In order to get intermolecular forces, what do I need to know about the molecule? And you can just say it. Type of bonds, but more importantly, the intermolecular forces is going to be determined by what of the molecule? By the structure, but yes. What? Polarity? So ultimately the polarity. So is it polar or not? If it's not polar, then the strongest intermolecular force you can have is the dispersion forces. If it's polar, then it could be either dipole-dipole or hydrogen bonding. Okay. So that's what we need to know about each one of these molecules, is we're going to need to look at them that way. So looking at this molecule, are there any that have only dispersion? Four made up of only carbon and hydrogen has only dispersion because it's a nonpolar molecule. All molecules that are only made of carbon and hydrogen are automatically nonpolar. Okay. So 4 would have dispersion forces. Any others that have only dispersion forces? Which one? Number 3. So are we all agreed that 3 and 4 just have dispersion forces? So where are they going to occur then in terms of boiling point? At the top or the bottom? At the bottom, they're going to have the lowest boiling point. So, okay, so 3 and 4 are going to be at the bottom. We're all agreed with that? And we all understand why? Because if you don't, you got to yell. Okay. We'll come back to in a minute as to how we're going to break that tie. But how about B? What's the strongest intermolecular force for B? What's the strongest intermolecular force? Dipole-dipole? Hydrogen bonding? Okay. Next week I'll have these cards that you can hold up in case we don't want to push stuff out to your phone. But Today you'll just have to be brave and raise your hand on which one you think it is. So let me poll. So how many people think hydrogen bonding is the strongest for B? Okay. Dipole. Okay. So more dipole than hydrogen bonding. Okay. Let's come back to that. Number 1, or Roman numeral 1. What's its strongest intermolecular force? Hydrogen bonding. Does everybody agree with that? Nobody for just dipole? Okay. All right, so a couple things we have to deal with. Those two molecules, and you'll see that we jumped from Lewis dot structures to these condensed line bond structures really quickly, right? So if you're kind of looking at that going, oh, what is that? You're going to need to practice so that, remember, this is a CH3. Well, all of these are C's at the intersections and at the ends, and then you add enough hydrogens to get you to 4 bonds and only 4 bonds. Okay, because that's all hydrogen can have. It can't have 5 bonds. That violates the octet rule. It also violates the number 2 rule of taking organic chemistry. Rule number 1, don't take it unless you have to. Everybody probably has to, that's why they're here. Rule number 2, no 5 bonds to carbon. And then number 3 will be no primary carbocations, but we'll get to that. And I only have like 4. If I had 10, I could sell a t-shirt, but I only go to 4. So no 5 bonds to carbon. So that means you could go through here and write your CH2s. And when you're, for Wednesday, in chapter 2, we're going to talk about naming. And one of the things I suggested, I typed in the book, was that when you're starting to look at groups, which you have to for Wednesday, that if you need to take a minute and write the carbons and the hydrogens, do it, because if that helps you see the structure a little bit clearer, it's worth the 5 seconds that it takes to do that. So between these two, the strongest intermolecular force is dipole. Now, which one of these two has the higher boiling point? Number 1 or number 2? Let's do this. 1, 2, on 3. Right? 1, 2, 3. Okay. Anybody go for 2? Why does number 1 have the higher boiling point?
More branching you have, the lower the boiling point.
Okay. So the more branches it has, the lower the boiling point. 1 has no branches and 2 does have some. Why?
Well, it takes up more material, so it has more room for the dispersion.
Okay. So the idea of London dispersion forces is that if you have 2 molecules next to each other, they do not have a permanent dipole. That's why they're weak. But when 2 molecules come together, the electron clouds will orient themselves so that there is some positive charge on one side and some positive charge on the other side. And in chemistry, we use the delta term to indicate that that's some. So when you see delta plus, it's some plus, delta minus, some minus. We kind of saw that last time with the resonance structures, with the resonance hybrid. We're not concerned about the exact charge. We're concerned that there's just some. So when these 2 molecules come together, there's a little bit of delta positive, delta negative, so there's a little bit of an attractive force. The strength of that attractive force is going to be really proportional to the surface area that comes in contact. This molecule with a branch is going to kind of looks something like that. And so the more spherical it is, the less surface areas can contact together. So this would be the lowest boiling point, and then this would be number 3 in that list in the questions. Okay. Right. So the more branching, the lower the boiling point. Okay. Everybody with me so far?
This is made by possible hydrogen bonds,
So in this case, there are no hydrogen bonds.
like possible hydrogen bonds, does that matter?
There are no possible hydrogen bonds. Because that's the next thing we have to make sure everybody's on the same page with is, what is a hydrogen bond? So let me just take a step back because here's my silly example of how important delta plus, delta minus, plus one, minus one charges are. And when I teach general chemistry and I talk about Coulomb's law, right? Coulomb's law depends on the size of the charges and the distance between the charges as to how strong the attractive force is or how strong the repelling force is if they're the same charge. So what I say is, if a space alien came down and asked me, what is the most important concept in chemistry? You can only pick one. I would pick Coulomb's law, because Coulomb's law of attractive or repulsive forces, it tells us about intermolecular forces. It can tell us about acid-base chemistry. It can tell us about inductive forces that we'll get to, induction and resonance. So to me, that's one of the most important concepts that there is. And so in explaining intermolecular forces, we're really talking about Coulomb's law. What's the size of the charge and what's the distance between the charges? So when I have no dipole, no permanent dipole, and they're just existing for a split second as the molecules get closer together, that's weak. But now when we go to a dipole force, like we said this one only has dipole forces. First of all, we should identify, well, why does it only have dipole forces? First of all, it's a polar molecule. Right? So when I look at this molecule, I see basically the CH3 group is nonpolar. But the C double bond O, the oxygen is delta minus and the carbon is delta plus. Because a carbon-oxygen bond is what? It's a polar covalent bond. To be a polar molecule, you have to be polar covalent. No, sorry. To be a polar molecule, you have to have a polar covalent bond, at least one. And they can't cancel each other out. So actually, we have 3 polar covalent bonds. Because when a carbon's attached to oxygen, it becomes slightly positive and the oxygen becomes slightly negative. So the idea here is that we have these molecules. This molecule has overall delta minus and delta positive charge in the molecule. The delta minus up here and down here, and the delta plus over here and with this carbon. Can everybody see that? Did I bring my... If not, later I can pull it. I think, do I have an iPad with me? Yes. I can draw that structure out. We can see it in the reds and the blues. So that's a polar molecule, so it has a permanent dipole with it. So now I have a molecule, if I want to just draw it as a blob, I've got a molecule with a permanent delta minus and a permanent delta plus. It's not only there when the molecules get close. It's there permanently. So now those two molecules can attract each other because they now have a permanent delta plus, delta minus, so that they'll orient themselves so that the opposites attract. Because it's a permanent delta plus, by Coulomb's law, it's going to be a stronger attractive force. And the stronger attractive force is going to take more energy to overcome it, to move the molecule into the gas phase, or to get it moving past each other, which is melting. Okay. All right. Is everybody kind of with me there? So then there's degrees of dipole forces. Because if I could make this delta plus the strongest it can be, and I can make the delta minus the strongest it can be, then I will have the strongest dipole force available. And so what do we say? We say, well, if you have an atom attached to a hydrogen, and that hydrogen is now the greatest delta plus it can be, and the X atom is the greatest delta minus it can be, you now have the strongest dipole interaction that you can have. So we go to the periodic table, and what do we say? Well, the only way that we're going to have the strongest delta minus and delta plus is if I put the top 3 electronegative atoms in the X position. So that's where the oxygen, the nitrogen, and the fluorine come from. So if I put any one of those 3 atoms attached to a hydrogen, I now have the potential for a hydrogen bond, because I've got the greatest delta plus and the greatest delta minus charge, and so they're going to have the strongest Coulombic attraction. Okay. Still with me? Does that make sense? So when we go and we look at this molecule, and I'm just going to write it again. The question is, does this molecule have the ability to hydrogen bond? Yes? Okay. Now, in order for it to hydrogen bond, remember, we have to have the atom directly attached to a hydrogen. So, are there any oxygens that are directly attached to hydrogens? No. So, can this undergo hydrogen bonding? No. Okay. And the reason we're doing this is so that we're all on the same page, because the hydrogen bond occurs when that atom, this delta minus, is then attracted to a delta plus hydrogen. But the only way that we can get a hydrogen bond is to have, for instance, an oxygen attached to a hydrogen, but the hydrogen the oxygen is attracted to in the hydrogen bond must also be attached to an oxygen, a nitrogen, or a fluorine. So I think in the book what I said was we had to have the hydrogen bond has to be to the oxygen, nitrogen, or fluorine, but then the hydrogen that it's hydrogen bonded to also must be attached to an oxygen, a nitrogen, and a fluorine. So in this molecule, the only hydrogens are attached to carbon, and carbon is not one of those 3. So in this molecule, there's no OH to hydrogen bond. And even if there was, it could only be attracted to another OH hydrogen, not a CH. So this one does not have a hydrogen bond. All it's got is dipole-dipole. Does that make sense? Okay. So then the last molecule was what? This. Something like that. Give me a couple carbons and hydrogens. But it had that NH2. Now, how does it hydrogen bond with itself? Well, this hydrogen, actually, there's two ways for that molecule to hydrogen bond with itself. It could be attracted to, or could be hydrogen bonded to another NH. Like that. Or the hydrogen could be attracted to the carbon bless you. Or the hydrogen could be attracted to the carbonyl, what we call the carbonyl, the C double bond O group, that oxygen. So there's two ways for that molecule to form a hydrogen bond with itself. And so its strongest intermolecular force is hydrogen bonding. And in each one of these cases, the hydrogen is sitting in between two of F, N, or O. Does that make sense? So then going back to that problem, wherever it is, number one, the strongest interaction it can have with itself. And when it says highest to lowest boiling point, or when it says what's the strongest intermolecular force that this molecule can have with itself, what we have to remember is that when we draw a structure like any one of those, in that pure material, there's billions of those molecules. We only write one. So we just have to remember there's more than one there that's interacting. So number one, can hydrogen bond with itself? Strongest intermolecular force, going to take the most amount of energy to basically take a liquid molecule and break it apart into the gas phase. Number two has dipole-dipole. So it has the second strongest intermolecular force. Number four has only dispersion, but it's a straight chained alkane with no branches. So it has the most surface area. And then the branch chain number three has has a branch, so it's a little bit lower. Okay, so does that make sense? So really, when we're talking about higher or lower boiling points, I mean, it really just boils down to what. Yeah, it boils down to it. It's about intermolecular forces. So you have to identify what intermolecular force is going on, and we could talk about stronger intermolecular forces between two molecules. We could say, for instance, if I go back here, and I'll be recording the lectures from here on out, so if you fell asleep or kind of zoned out, you can go back and refresh yourself afterwards. It'll be by the end of the day that I'll put it back up again, now that I have the software on here, the new software, because the old one wouldn't work. So let's say we talk about solubilities of alcohols in water, right? So when we talk about what kinds of alcohols will dissolve in water, we're still talking about intermolecular forces. And then this gets us to the like dissolves like phenomenon, right? All like means is like what? Like intermolecular forces. So if the molecules have similar intermolecular forces, they will dissolve. And it's actually not even that it's not even that simple. Because what we're really talking about is I'm going to have to, if I take ethanol here and I take water, I'm going to have to break the ethanol molecules apart, break the waters apart, bring them together, and hopefully when I bring them together, the intermolecular forces that they experience is at least the same as the two intermolecular forces that I broke apart. Otherwise, it won't dissolve. So ethanol dissolves in water, right? Up to 99%. Right? That'd be like 198 proof. So we can dissolve ethanol in water infinitely. But as I make this chain longer, that chain then undergoes dispersion forces, or it's a nonpolar part of the molecule. So at some point, that chain can be long enough where the alcohol will not dissolve in water. Yeah, the OH might want a hydrogen bond with the water, but the nonpolar part of the molecule, if it's too much, then it will not dissolve in water. And we'll find out, I think we'll find out in lab that that's about 4 carbons. That when you get to 4 carbons, it really doesn't dissolve in water well. But what would be the intermolecular forces? The carbon attached to the OH, then the oxygen could be bonded to the water hydrogen, or its hydrogen could be hydrogen bonded to the water molecule. Again, these are the hydrogen bonds that are possible, and in each case, that hydrogen is sitting in between 2 O's, N's, F's, or combinations of them. So that's how we look at solubility as well.
Why would a longer chain make it less soluble?
Well, because the longer chain becomes what we call hydrophobic. It's the nonpolar part. And so what we really have to do is we have to take all of the alcohol molecules, break them apart, break the water molecules apart, and then mix them together. And what happens is that you don't get enough energy back from, if the chain's too long there, the long chained alcohol interacting with water isn't stable enough to break the water molecules apart. Is basically the way we look at it. I think I had a slide on here. So, well, that's why ionics dissolve here. So here's kind of that reasoning. So the green things are the nonpolar groups. Even if I put a nice OH group here, it wouldn't take a whole lot of energy to break the long-chained alcohol molecules apart. But the problem is breaking them apart, that's not the energy that I'm going to need. I need to overcome the energy of breaking these apart, breaking the waters apart, and then having enough intermolecular forces between the long-chained alcohols and the water to make up for breaking the waters apart. This example is like for a nonpolar solid. Why does a nonpolar solid not dissolve in water? Well, it's unlike, right? It's not like dissolves like. This is two unlikes, so they're not going to dissolve. But that's not really the detailed reason. The detailed reason is going to have to do with energy. Because in chemistry, energy gives you the reasons for everything, right? Just like in politics, you follow the money. In chemistry, you follow the energy. So the energy problem here is that my nonpolar solvents don't form intermolecular attractions with water that are strong enough to break the waters apart. So it's not that I can't break the nonpolar solvents apart, because I can do that all day. It doesn't take much energy. The problem is when the nonpolar solid and the water interact, there's not enough energy there to break apart the waters. They don't want to come apart. The same thing would be true if that long-chained alcohol got big enough.
What do you mean by break the waters apart?
Meaning that these molecules are going to be interspersed within the water, so that like it would be here and it would be attracted to the water. Because it's really a total sum of energies. So I don't get enough energy out here to make up for what it costs me to break the water from another water. But all of this depends on, is the molecule polar or not? If it's not polar, pretty straightforward, you got dispersion. The more surface area, the more attractive force. But it's dispersion. So you can have long chains of carbon in waxes, but they're waxes. You don't have to heat them up very, very much to get them to melt. When we go to dipoles, we have to look for hydrogen bonds. And when we look for hydrogen bonds, that's where we need to see the hydrogen in between those two ON or F atoms. So that's intermolecular forces in a nutshell. In order to get there, you got to get the dipole, whether the molecule's dipole or polar or nonpolar. In order to get to there, we need to talk about whether or not the molecule is truly polar. So one thing I'll reinforce is that molecule polar? Yes or no? Yes? Everybody agree it's polar? Anybody want to say no? I'll say no. Wait, these dipoles cancel.
The loads of electrons create on the oxygen create repulsion. So the shape is actually bent instead of linear, and the bent shape makes it have the oxygen have partial negative charge, and the hydrogen have a partial positive charge, making it positive.
Okay. Which I would boil down to one thing. You didn't write the Vesper geometry of this molecule. You wrote a Lewis dot structure. Now, first of all, it's water, right? So when I did that, you're like, you got to be out of your mind. Water. I mean, if water isn't polar, then everything I've learned in chemistry is wrong. And it's been a lot of people lying to you if water is not polar. But I love to do this to freshmen because I'll say, oh, is that polar? And some people go, no, it's linear. And then I'll do this. Then I'll say, is this one polar? And they'll say, well, yes. And what am I doing here? I'm reinforcing the idea that before you get to whether the molecule is polar or not, you got to have a Lewis dot structure, and then you have to put it into a Vesper geometry. If you don't put it into Vesper geometry, then you can't determine whether it's polar or not. Now, what I would do is I would say, here's my water molecule with my lone pairs here and here. Now, that structure that I just drew is a tetrahedral structure. And we're going to be drawing this a lot, so I might as well introduce it now. These two bonds that are normal are just regular bonds. They're in the plane of the screen. The bold wedge is in front of the screen. Take me a minute to get back there. Stop. This one is in front, and this one is behind. So the way I'm going to represent a tetrahedron in three-dimensional space on a two-dimensional surface is two bonds in the plane, a bold wedge in front, and a dashed wedge in back. And so that's a tetrahedron. When I do that, when you're trying to determine if it's polar or not, the lone pairs don't count. I think there's some controversy sometimes about whether the lone pairs count or not. They don't count. The only thing that counts is these two bond dipoles, and then we would take the vector sum of those, which would look like this. And basically what that means is the delta plus is around the hydrogens, and the delta minus charge is around the oxygens. And a molecule that has some delta, has different charge distribution on its surface is polar. So in order to determine polarity, we've got to put it into a Vesper geometry. But in order to do that, we need the Lewis dot structure. And was it clear when because I added in the book, if the structure's symmetrical with all the atoms being the same, it's not polar. So really, any of those geometric shapes, the linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral, any of those shapes where there's atoms there and it's symmetrical is nonpolar. If it's unsymmetrical, it's going to be polar, as long as it has a polar covalent bond. So we really don't have to draw out these vector sums. We can just say, all right, is it symmetrical? It's nonpolar. If it's not symmetrical, it is polar. So the example that I showed was if I put 4 carbons, if I put 4 chlorines around a carbon, yes, that molecule has polar covalent bonds, but they all cancel out since the molecule is symmetrical. And I think I showed you the molecule where they're all it's all the same shade of green. Yes, no. If you refresh chapter 1, it'll show up. That's why I'm asking, because I think what happened was I put it in after people started, and then it says they need to refresh in order to. So it's there. But in this case, that carbon chlorine Hey, what am I saying? I have the book. I don't know what version of the book I have. So molecules like that that have slightly negative and slightly positive, they're automatically going to be polar. But a molecule that doesn't change is going to be nonpolar. Oh, maybe I'm going to have to refresh. The thing is, I don't know how to refresh. It was there. I pasted it there. So I'd have to refresh and see it. However you do that. Okay, so were there any other questions about polarity?
I think it was number 25. It had to do with hybridization and what
Oh yeah, that one.
electrons are in what orbital.
Yes.
And I understand how you know that like an atom sp3 hybridizes with other sp2 hybridizes. I just don't understand how you know like what and how many electrons are in which orbitals and when there's still like a 2p orbital.
Okay. Number 25. Yes. Okay, come on. That was it was a selenium ion. Wait, I'm way too far down. So it was a H attached to a C, triple bonded to an O with a plus charge. There it is, right there. That a selenium ion. So I'm just going to write it. First of all, there's a typo because it has 3 hydrogens attached to a carbon that's triply bonded. By my count, that's 6 bonds, which is 12 electrons, which violates rule number 2 of organic chemistry. It's expanding an octet that can't be expanded. So the correct structure is H attached to C attached to O. So let me go back here. So H attached to C, triple bonded to an O, plus. And the question is, what does the electron configuration of the oxygen look like? So let's go through this step by step. I have questions. My first question is, what is the hybridization of oxygen? And, sorry, missing the lone pair. So what's the hybridization of the oxygen? SP? Do we agree? Do we know how she got that? Okay. How did you get that?
So I counted the triple bonds as like 1, and then the lone pair as 2, and then I always do 1 less with hybridization.
Okay. The one less part's throwing me, but it's okay. Did I do the formula for non-carbon atoms as to how many hybrid orbitals there are last time? Yes. So that formula was what? The number of hybrid orbitals for any atom is equal to what? Number of sigma bonds plus the number of lone pairs. So that's exactly what you said up until the minus part. So we have 1 sigma bond. So the triple bond is treated as 1 bond. The lone pair is a second. So this has 2 hybrid orbitals. So 2 hybrid orbitals means what? S and P. So that oxygen then is sp hybridized. So it'll have 2 sp hybrid orbitals, and it will have 2 then unhybridized p orbitals. Now, did I also say last time where the lone pairs go? Lone pairs go in what orbital? The p or the hybrid? I didn't. It's possible. See, I can't. This is a bad week because everybody wants to switch their classes, and there's 15,000 things in my head, and it's bad enough when there's 2. So I have a hard time remembering what I did in the 8 and the 1 o'clock class. So hybrid lone pairs always go in the hybrid orbitals. Okay. So that formula is the first part to know about this problem. The second thing is that we've got to put the lone pairs in the hybrid orbitals. And you may ask, well, why can't they go in the p orbitals? And the answer is because if I'm going to overlap 2 p orbitals, and one p orbital has a pair, and the other p orbital has 1, I can't share 2. Right? So the only way we take p orbitals and form pi bonds is if each one has 1 electron. Okay? So lone pairs cannot go in the p orbitals. They must go in the hybridized orbitals. So that means this is in an sp hybrid orbital. Okay. So how many total electrons are in this oxygen atom? And what I wrote here, a diagram like this where you've got an sp, a p, that diagram is a diagram for any sp hybridized atom. It's got 2 sps and 2 unhybridized ps. What's different is each element has a different number of electrons that I'm going to put around that shell. So how many electrons are in that oxygen? How many electrons are in that oxygen plus? Because that's what it is. Take one away. 5. So there's 5 electrons in that oxygen plus. So if I'm putting them into these orbitals and I automatically have to put the lone pair in the hybrid orbital, then there's 2 of the 5. There's 1 there, and 1 there. So there's my 5 electrons. 2 in the p's, and then in the sps, 1 unpaired and 1 pair. And then on the other side, I'd have an sp hybridized carbon, which I might as well just draw out quickly. Here's my sp hybridized carbon with my 2 sps and my 2 unhybridized ps. That carbon has 4 electrons because it's neutral. So that means 1 electron in each of the orbitals. And when I form the carbon-oxygen bond, I'm going to pair these guys up. I'm going to pair the p orbitals that are parallel, the other p orbitals that are parallel. Oh, stop. And then my H, my spherical H over here on the other SP. Now, I didn't answer question 25 yet, but I'm close. Does everybody kind of understand? So you have to remember the formula. When you look at a structure, The formula is going to tell you how many hybrid orbitals are there, which is going to tell you hybridization. You can sketch out the orbital picture in order to show how they overlap. The critical part now is oxygen has 2 sp orbitals and 2 unhybridized p's. Where do the electrons go? In the sp, I've got 1 unpaired, 1 lone pair, 1 unpaired in each of the p's. So that would be the diagram that would go with that in 25. That would go with that oxygen atom. Does that kind of make sense? Okay. For Wednesday, we have chapter 2, 1 through 5. I've already annotated it. And then that also means that when I annotate the next sections, we have to be able to refresh to see what I put on there. So I'll have to figure that out over the weekend. The chapter 1 problems will be due by Wednesday, the homework problems at the end. And let me just point out something, that I can't break the chapter problems up when they're due, like in the middle. So all the chapter problems have to be due at the same time. So just think about that in the future. That means if there's a problem you don't quite understand before coming to class, all those problems are not due until we finish the chapter. So you could leave it, and then we can talk about it, and then you could go back and answer it. Remember, this is all low-stakes stuff, so it's just a few points, but you don't necessarily have to answer those problems, but it would be really helpful, coming to class. So if you don't get something, ask, but at the end of the chapter, that's when all of the problems are due. Okay. All right, so if you have any questions over the weekend and stuff, email me, stop by. Otherwise, I'll see you on Wednesday.
For some reason, I can't seem to pull up chapter 1 anymore. Like in class,